in other areas. So thanks again today for joining us, Professor Kiss, and the floor is yours. Okay, thank you.
Thank you very much for the invitation. I've already seen that my colleague was here a few weeks ago, Jacopo Jacopini. I'm not going to talk about higher order dynamics. I'm going to talk about sort of two different projects that I've been working on recently. But before I do that, let me just maybe briefly tell you about sort of this new exciting adventure of the Network Science Institute. So the sort of mothership, if you like, is in Boston, and then they have two new sites, one in London, where I started working sort of 2 years ago. Before that, I was at Sussex University. I'm a mathematician by training, and there's also a hub in Portland. So yeah, this is some exciting developments regarding the institute. So this is how we currently are at Northeastern University London. So we are 5 faculty. I think you saw Jacopo, maybe you know some of them. We have 9 PhD students, which is going to grow further, and also sort of 3 postdocs currently. So it's a very, very exciting new start, and I'm very excited to be part of it. I mentioned to Paolo already that we're also organizing a seminar series. I don't know whether you are getting our emails or not, but the plan is that you are going to get them one way or another. Hopefully you are going to look at them with interest rather than deleting them. But we have 2 regular seminar series. There is one regular bi-weekly seminars, and we try to invite lots of young sort of developing sort of early career researchers. And also we have a distinguished seminar series, and some of these in the past were Vittoria Colisa as part of the opening the British chapter of Network Science Society, obviously here in the UK, and then Martin Korschey from Vienna, and Alain Barat from France more recently. And we also have a very exciting sort of visiting programs. There are lots of sort of PhD students and master students from all over the world visiting us. So we are just reaching out. Please come and also visit us and work with us. Okay, so enough of marketing. So I'm going to talk about 2 different problems, if time allows me. And the first one is detecting patterns in global shipping networks. And this project has started many, many years ago. It was a conversation that was at the school gate with a friend of mine. He says, hey, I have a lot of data about how ships are moving around, carrying crude oil. It would be so nice, maybe you are doing this network analysis, maybe you can do something with this data, and you can give me some insights. And my God, it took a very long time to actually sort of make it happen and start to generate some results. But basically, the data is fairly standard. So you have these are ship types. So there are Aframax, Panamax, Suezmax, very large crude carriers. Basically, just think of it as ships with different capacity, sort of from small to the extreme to the very large. And then here we have sort of information about, they went from one port to another, and then also the region where these ports are. And then we have other information about what the cargo was and what was the quantity and stuff like that. So basically, the way how we try to think about it is that basically we are tracking the movement of ships. So for example, you have a ship here, he starts, and actually these journeys are very interesting because these networks, these edges in the network are not uniform. So this is what we call a laden leg. So when the ship carries goods, and usually a laden leg is followed by a ballast, by an empty leg. So basically the ship then goes out and, looks for cargo again, and then another ballast usually, and then, another laden one, and then ballast, and so on. So basically it's like a weighted, directed, time-stamped, and actually the weight has meaning as well, whether if it's laden or ballast, right? So it's fairly intricate. And then the question is, how do you analyze this? Do you look at the ship level? Do you look at the system as a whole, since this is like a physical system with a given number of ships, and ships at any point in time, they must be somewhere, right? They cannot disappear. So we decided to kind of deal with this in 2 ways. So first we started looking at the ship level characteristics. So what people are interested in, so people who are interested about profits and economics, is I want my ship to spend as much time as possible laden, right? Versus then sort of searching cargo. So we just looked a little bit at this, and then we try to understand and see if there is any pattern. So these are the sort of blue violin plots here, and then you can see a variation. As I said, these are basically ship types of different capacities, and what you can see that there are some classes are doing better than the other. For example, here VLCCs are doing rather well. And then we're also looking at things like number of unique regions visited. So we're interested in see how much do the ships actually go around. So do they tend to stick in the same area and do a lot of repeat journeys, or do they kind of go out there and they are seeking that cargo and they are being adventurous, right? So this is like a ship-centric analysis to try to understand how these ships perform with respect to each other and also within each category. And obviously, this is also linked to not just to profit, but also environmental advantage. You don't want your ship to kind of, sail around empty. So how do we sort of make this more mathematical, right? To understand, for example, this visiting pattern and exploration pattern. And in order to do this, we have to look at something which is called higher order networks. And higher order networks is a very inflated term, because I think people are using it for lots of different things. So higher order is also probably what Jacopo said was maintaining higher order. And then here higher order is more like something to do with time. And especially I'm thinking of non-Markovianity. So here you can think about it simply. If I, for example, want to predict, I'm in a current port right now and I want to see where will I be going next, then it turns out very quickly that in order to make a good prediction, then you need more information than just the current port, right? So you need to kind of go back in time, and that's why we call it kind of higher order. You need to go back multiple steps. Are you familiar with this concept? No. Okay, so that's good. So here is a simple example where basically this is our data, right? So I have, a ship going from port A to port M and to X, and then you have basically all these journeys. Now, if you are going to build a network in the classical sense, what do? Well, you basically have all these journeys, A to M, M to X, B to M, M to Y, and you just count up how many journeys have happened between the respective ports. And then what your prediction tells you is that it's 50-50. If you are in M, then with 50% probability you go to X, and with 50% probability you go to Y. But that's not the case, because if you take into consideration that the ship is right now is in A, but it came from M, then you can make a much better prediction, because what you notice is that having been in M previously gives you 75% X and only 25Y. This is obviously a baby, a toy example, right? But kind of that's the idea. So you need to go back in the past to kind of learn what the ship was doing. So what we say, rather than looking at the network in this way, so in this very sort of simplistic way, sort of pairwise interaction, if you want, it's better to look like this. Now you are inflating a node, and a node is no longer a node in the sense of classical graph theory, but now a node actually is a link that appears very frequently, and it has a good ability to tell you where you are going to go next. So basically, it's a bit like, I'm in A, I'm in M now, conditional that I've been in A before, and then my next journey is going to be M to X. So basically, a network like this is a much better representation than this. But what happens is computationally, if you want to do this, then basically you are inflating the state of the, rather than having n nodes, now you're going to have also the edges, and there is some rigor and there is not much rigor. I mean, there are some very nice papers. Actually, I didn't put one of them here by Ingo Scholz, where he talks about a multi-order interpretation of this. Basically, you are building these networks with sort of more inflated nodes, and if you make the network more complicated, no Markovianity becomes Markovian, but you are paying the price of having an expanded state space. Okay, so I think this is okay. So what then we set out to do is to try to understand, not necessarily about prediction, because I don't think that prediction is something that's very interesting, because somebody said, ships are just chasing the dollar. They don't really care about mathematical prediction, But in terms of exploring, what we saw that would be very nice is to understand that if we are looking at least over a path of length, sort of 2, so 3 nodes and 2 edges, then are we going to find sort of different densities and different frequencies of how ships move around? So for example, this ABC means that they go between distinct regions all the time, right? So they go from A to B to C. It doesn't matter what is the precise region as long as they are different. Or it could be that they go to A and then they go from A, they go to B, but in the B they do a sort of self loop, because we're talking about regions here. So the regions are large, so you can go between ports in the same region. So these are all the possibilities that you can have over 3 nodes. And then when we started looking at the frequency of this over time, then what we noticed that these are pretty kind of constant over time, which in a way is good. There's some kind of statistical equilibrium, if you like. But then, when you go to people who are interested in this, and then so what? What can you do with this? And then what we decided to do, we said, let's look at the performance of top 100 versus bottom 100 ships. And then when we did that, we noticed something very interesting. So look at the top 100. So top 100, they prefer this sort of circle here has a much bigger radius. So more percentage of journeys made by these ships tend to be of the sort of varying type ABC, whereas the sort of bottom performing, they seem to like sort of moving within the same region, right? So basically, diversity and exploration somehow is correlated with performance and being able to be loaded most of the time rather than seeking cargo. So what did we learn from this? Diversification of routes, journeys is a key component. So it looks like those who are sort of a bit more adventurous, they are doing better. This is a bit technical, I'm not going to go into that. We did a bit of estimation that if the bottom ships would kind of take the strategy of the top performing one, that there could be a lot of savings be made in terms of environmental impact and so on. And basically, in some sense, you can look at the top performing ships as a kind of model. But of course, economically, this competition and supply and demand is not just easy as sort of copying a strategy, right? Because when you change a strategy, then the others change it as well. So it might only work on a very short time scale. Okay, so this was all very ship centric, right? So we didn't look at the network as a whole. And what happens if we look at the network as a whole? So this is a little video of the activity. So as I said, these are ships that are traveling around the world, right? And the ship is always somewhere. It's either in the sea or it's in a port, right? But this is a closed system. And then basically you have this kind of heartbeat kind of activity. And the question is, how can we analyze this all at once and try to get some kind of idea about what the global patterns and the global trends are? So to do this, what we have done is we have divided, basically we had port level information, but we grouped those ports into regions. We had a sort of moving average of activity. So these are just some sort of sketches on the various regions, how the time evolution looks like. And then basically what we want to do is we want to analyze all these signals at the same time. So like a spatial temporal signal, right? Because being in a region and then you have the time evolution, then basically like a spatial temporal region, and I want to do it, analyze it at the same time. But before we do that, we remove some kind of linear trends because actually some regions sort of show growth in demand and supply and stuff like that. So we want to make sure that analysis kind of makes sense. So to do this, we are using this dynamic mode decomposition, which I'm pretty sure that you are familiar with, right? This is a kind of Fourier series on steroids. But if not, then you can look at this paper. Basically I'm not a sort of super expert at this either, but I'm using it myself as well. But the idea is that basically if you look this kind of decomposition, what this analysis allows you is to identify some dominant modes across the whole world, and it can give you the period of these modes. So of this kind of behavior, it tells you how often this kind of pattern repeats, and also gives you information about the differences between different regions. Okay. So when we do this, the fitting is rather pleasing. I mean, most cases is about, I don't know, R square about 0.7 or so. So there's a good reconstruction for most of the regions. I mean, of course, the data is very noisy. And in terms of patterns, and this is the kind of plot that we can produce. So for example, here, and I'm going to explain. So this is basically what we are fitting to our signal in space and time. And this tau j here, this is the period. So for example, this is roughly half a year. In this situation is like sort of 4 months, 3 to 4 months, and this is like a yearly period, right? Then the amplitude, this A and J is basically the amplitude is the activity in every region, as you have seen it before. And the amplitude here is encoded by the size of the marker, right? The bigger the marker, the more activity there is. And this hue in colors that you can see between different regions, so you can see this kind of color coding is the kind of delay between the various regions. So this is measured in weeks. So for example, you can see that between kind of pinkish and bluish, greenish, it could be a delay of 5 weeks, right? So in terms of levels of activity. Okay. So these are the kind of modes that we picked out to be the kind of most dominant, and then we can we can actually associate a little bit of story with each of these. I'm not going to go into much details, but if you talk to kind of specialists in data, they can say, okay, yes, this related to the climate, and then it's related to the fact that they need to heat, they need to use their cars. There is a kind of natural cycle, you know, around the world. But maybe just talk a little bit more about this. So when we look a little bit more in detail, especially at this half a year and sort of 4-year period, then what we notice is that we can find sort of legs of 6 to 8 weeks between Middle East and Southeast Asia, which basically means that sort of Middle East and Southeast Asia, there is a difference of sort of 6 to 8 weeks, which correlates with the time it takes to carry the crude oil from one place to another. Because these, you know, they take quite a long time to travel, plus there is loading, plus sometimes they wait in the port and they try to get a better price and so on and so forth. So basically, this I was kind of very pleased with this when we found this method, because, you know, the ship-centric was nice, but it also, we wanted to have something that gives us information at the whole system level. Okay, so any questions? By the way, feel free to stop me at any point and we can kind of turn it into a discussion if you like as well, if you have questions.
I guess just a follow-up since is there some kind of patterns in terms that you in the terms that you just said, like in terms of causality patterns of routes that are clearly established that we can recognize here, apart from the one you just said, like is there like looking at also the reconstruction of the time series, is there any kind of clear sequence?
To be honest, we spent a lot of time trying to kind of look at the data and look at what we find and then kind of relate it to real life things. So for example, with the yearly pattern, where is the yearly pattern? With the yearly pattern is what you notice is that there is very strong correlation in activity, those who are close to the equator, right? So these are all kind of, the amplitude is very high. So there's high level of activity here. And then there is, for example, very low activity in the southern hemisphere, which is again related to kind of the weather cycle and climate and the supply and demand for the main things. So such as heating and cooling, and also the amount of you know, the use of cars and sort of stuff like that. But I think it's very difficult to actually go and sort of pick out individual routes and to say, oh, I think this is sort of more significant or dominates with respect to other and stuff like that. So I think that was more from the ship kind of perspective. Is more suitable to do it in that kind of way. Here, global is more difficult to pick out certain things. Okay, so you mentioned machine learning and stochastic processes and all that stuff. So let me move on to the second topic, and this is about learning networks through dynamics on the network. So this is just an evidence that this is still a very active area. But what I'm trying to say here is that I think it is extremely active. The people are very interested in that. If you have a dynamical process, it could be discrete, continuous, stochastic, playing out on a network. And let's say you only observe the process itself, but not the network. Then the question is, can you reconstruct the network or not? Or would you want to reconstruct the network or not? Some people, for example, say, for example, here is the predicting network dynamics without requiring the knowledge of interaction graph, right? So in some cases, you can do good prediction of where the process goes next without having kind of full information of the network. But I think from a mathematical point of view, it's still very interesting to say, let's simulate something on a graph and then pretend that we don't know the graph, which in most real life, we don't know the graph, but we observe the process and ask the question, can I reconstruct the graph or not? So that's kind of the big question. And I think this is extremely active area of research right now, reconstructability versus predictability. Probably you know this better than me because some of you are statistical physicists. So basically, this is almost like the forward model, right? So this is a contact matrix. So for example, you could say this is the mixing between individuals in different age categories, right? This is just a network. And then what do? I run an epidemic on it, like a simulation, a Gillespie algorithm, and I run an epidemic. And then I end up with some nice epidemic curves. And what I want to ask, can I reverse this process? What if I only have this? Can I reconstruct the graph or not? So that's kind of my my question. And basically, I'm going to tell you about one way how I hope that I brought a sort of fresh perspective to this question. And why is it hard? It is hard because are you familiar with epidemic models like SIS and SIR? Right? I don't want to explain what that means. But I'm a mathematician, so when I started doing this about 15 or 20 years ago, I thought to myself, but what is the exact model? Because many people came up with this mean field model, like the limiting models, sort of averaged over the whole system. And I say, but where do they come from? Do they just appear out of thin air, or are they derived from somewhere? And then I started looking at the exact models and try to understand whether I can derive these models. And probably this is the simplest graph, right? Only two nodes linked by a node. And I want to simulate an SIR epidemic on this. And guess what? I need 3 to the 2 states. I have all the possible labeling, right? Already it's a 9-dimensional system, even though it's linear, but it's very complicated, right? Now, can you imagine if I make a network of 100, then I count 3 to 100 state space, basically the dimensionality and the complexity kills me. And you cannot do it even computationally. And of course, you need some approximations, closures. I don't want to talk about this. I wrote a book about it. sorry to sort of for more marketing. But yeah, so there are different approaches how you can try to do this. Start with the full state space, or start from the bottom up and sort of try to come up with sort of clever tricks of basically cutting the complexity of the system. But what I want to do here is literally imagine that this is a simulation, my Gillespie simulation, and these red dots is where I'm sampling the epidemic. And my question is, if I only have this information, can I say something about what was the underlying net that generated this signal? So I think it's a very tough question, and most people say that probably you can't do. But why so complicated? So why is not possible? Maybe what I forgot to say that in this case it's very simple, because at least we can count. So what's driving the epidemic? The epidemic is driven by the number of SI links, right? That's where the reaction happens. The more SI links I have, the more reaction I have. But situations are very complicated, because you generate a graph and then you see the epidemic somewhere, and then the epidemic spreads. And then what you see here, I have one epidemic and I have 2 links that can generate further reactions, right? So only this link can fire and that link can fire. Then the disease spreads one more time, and now I have a 2, and now I have a 6. So if you count up all the SI links, then I have 6. Now, but if I do the same, because it's stochastic simulation, and now I infect the node, let's say on the right, not on the left, now I still have 2 infectious nodes, but I have only 3 infectious links, right? This would not happen on a fully connected graph. On a fully connected graph, if you have k infected, then you have m minus k susceptibles, and you multiply the 2 together and you have perfect counting. But here you can't count because of the stochasticity of the process itself. As the process unfolds, always lays down slightly different configurations. And more than that, there's also stochasticity in the network when you generate it, right? And because we cannot count SI links, that's driving the epidemic. That's why I cannot sort of formulate good models, right? So I want to simplify my life a little bit, and of course, I'm not going to be able to infer edges in the graph, whether an edge exists or not. But what I say, let's assume that my whole universe of networks is made up of regular Erdős-Rényi and Barabasi-Albert. Do you know what these are, roughly? So regular, obviously, is all about contact heterogeneity, right? Regular, everybody has the same number of links. Erdős-Rényi, you flip a coin, every possible link is probability P, so it's random network. And Barabasi-Albert, this is the scale free, it's the rich get richer kind of network with lots of heterogeneity. And I'm setting myself the challenge, as I said, I observe only these red dots, and I want to be able to say whether the network that generated the data is one of the 3 types. So how do I go about it? Well, I want to cheat, and I want to kind of do it in the kind of, you can think of the epidemic as a birth and death process, right? When you have a new infection, it's like a birth, and then there's a recovery, then it's a death. And a birth and death process on a fully connected sort of graph is very beautiful, because it only has state space n+1. You either have 0 infected, 1, or everybody's infected. But what is stopping us using that model? Well, is the fact that we cannot count how many SI links we have, right? When I have k infections on the graph, I do not know what the pressure is going to be because it's stochastic, right? Not only that it's stochastic, but it depends on the previous state. It's kind of no Markovian in some sense. But I still want to use, so this is what I want to use. That's how the forward Kolmogorov equation would look like for the probability that I have K infectious at time t. And these are the rates, rate of infection from K minus 1 going up to K. This is you are leaving the state with these rates, and then you have a recovery. The CK, we know this, but we do not know who these rates are. For a fully connected graph, this is easy because it's simply K times N minus K multiplied by the rate. So now I'm going to do something sort of interesting. I didn't know if it's going to work or not, but I say I want to use this framework, but I need to do something about those rates. So I said to myself, okay, why don't we learn the rates? Let's do a lot of simulations and try to learn what these rates are. So what do? I choose a network family, all three, set a bunch of parameters, set them to particular values, run a lot of Gillespie simulations, and basically record everything. Record the time of reaction, how many infections I have, how many SI, how much time I spent in a state, and all this kind of stuff, right? And then basically, I am counting. I'm counting what is my reaction, what is my rate. Now, this is quite interesting. So what these graphs are showing here, let's pick this one. It says that when I have 73 infectious guys on a graph of maybe 1,000 nodes, these are all the possible counts that I can experience for my rate. So it ranges from, I don't know, 350 to 410, right? And then I don't have time to go into this, but you have to take a view, and then we are doing a clever averaging. We are going to say, I don't want to deal with this because I only want a number, right? When I have K, I need to know exactly what's my rate of infection. And I do this, what is called like a time-weighted average, right? I'm multiplying the counts by the time the Markov chain spent in the state, and then I'm plotting them sort of in this way. And what is surprising, first of all, so those kind of, those are the recovered values by using this approximation. And what we notice straight away is that these curves seem to look differently depending on which graph I'm using, right? So what do we notice? That the Barabashi-Albert kind of leans to the right. The regular the regular actually leans to the right. Barabashi-Albert rises early, and then the Erdős chain is somewhere in the middle, right? And from a kind of machine learning perspective, this is good, right? I have some curves which look slightly different. And the question is, how can I learn these curves? Because if I could learn them, then we are onto something. So what do we do? Okay, first of all, I was kind of jumped ahead of myself. First of all, I need to test whether what I'm measuring makes sense. So basically what you do is you take these values measured computationally, and you plug them into this kind of, let's call this a fake Kolmogorov equation, because it's not, we do not have mathematical Kolmogorov equation, but let me plug all these AK heads in there. And if I plug them in there and I solve the system and I compare it to the true simulation, the agreement is excellent, which basically says that this is a good approximation. I cannot prove it, I don't know why, but it works. And I'm amazed that it works because of what I said before, that the AK is correlated. Of course, if AK is high, then the next step is also going to be high, and there is some spread around it, and so on and so forth, right? So mathematically, this is completely non-trivial. Okay, so as I said, we see that these curves are different, but how can we put some kind of parametric model to it? Because just by looking at it, it's not really helpful, right? So what we do is we propose a model that looks like this. So C, this is simple scaling, because if you have a high infection or low infection, kind of, it allows you to adjust it. This Kn minus K comes from the fully connected graph, but I put a power here because the power allows me to make it peakier or flatter. And then I also have a shift, right? So this term is for the shifts to make sure that I can shift the curve left to right. And so I have a scaling, a power, and this sort of shift, this CP alpha. And guess what? For every simulation that I do, I fit with a simple, a simple regression. I fit to this curve, and when I plot the estimated values, and I get something like this. It's absolutely beautiful, right? In the C, alpha and p parameter space, the three graphs, they sit in completely different parts of the space. So it says, okay, this is great. This is learnable, and this is a good model, right? So what I meant is that it was simple least square, right? We just found the C, P, and alpha that was closest to the data. So we can distinguish between network classes. So what do we do now? So what we do now, we do use some kernel density estimator to feed this, and we are going to say that these are my priors, right? And let's set up the inference with this prior. So that's my data, as I said before. And the way how we do it, this is straightforward. This is the jumps between Markov chain, right? States of Markov chain, which is non-trivial numerically. And then what I say, my priors are of these three types, regular, Erdős-Rényi, Barabashi. I give a third weight to each of them, and then I use the Bayesian framework, and I invert it, and I say, what's the probability of the model given the data that I observed? And lo and behold, it's pretty good. So what we can see here is basically, these are simulations, data taken from Erdős-Rényi, and the posterior. Yeah, these are the posteriors. So the probability of getting Erdős-Rényi, Barabashi, these are always add up to 1, right? So the three posteriors are here. So the Erdős-Rényi dominates. Here, when we simulate it on regular, then the regular dominates, and the Barabashi Albert kind of takes it all because it's highly heterogeneous, and that's easier to distinguish. I mean, the method is not perfect because there are some issues about sort of confusion, which you expect. Because, for example, if you have an Erdős-Rényi and you make P very high, and regular you make very dense, and they're going to be very close. But if you look on the main diagonal, these values are not bad at all, sort of 70%, 85, 90%, right? And then we've done some further tests for more theoretical things, which again, this seems to be working well, and also on some real networks. And then, yeah, you were a bit disappointed that we only got into scientific reports with this, because I felt that this was a very, very kind of cool idea, but maybe next time. We were aiming much higher, but unfortunately we didn't get into top journal. You can do also something else. You can kind of flip it if you like, and you can say, what about predictions? Because what I've done here, I observed the whole epidemic, which is very rarely the case, right? If you have an epidemic starting tomorrow, I hope not, then you are only going to have very little data, right? And what we show that with the same framework, you are not doing too badly. And here there's, again, a lot of technicality about how you go from estimating parameters and how you then translate that into, because you need to, whatever you're estimating in terms of parameters, you need to put them through the forward operator, right? And then your uncertainty has to be viewed through projecting all those parameters forward, and that can kind of change a lot. And then, if you want to check out the paper, then you can have a look. But anyway, the message here is that the more data you have, the better the prediction, right? So if you go from left to right, here I have very little data. So the estimation, the confidence interval, credible intervals are quite high. And then the more data I get, so what this says that I have data up to this point, right? So the more data you have, the more you can kind of predict. So yeah, it kind of works good. So any questions? Or can I conclude? I think I'm doing okay with time, no? Yeah, perfect.
Yeah.
So what are okay, so, I forgot to turn my conclusion around. So maybe actually it's okay like this, because we finished with the epidemic inference. So I think there is promising potential in learning network structure. And I was talking to somebody who's an expert in Bayesian analysis, and they said that computationally this is becoming more and more fashionable in many cases. There is nothing wrong with coming up and learning very good and very informative priors, right? And I think that in network science, this is somehow a bit underexploited. If there is a sort of range of models of networks and stuff, why not hit them with with SIR, with social adoption, with other kind of models, and sort of see what happens, and see what we learn by actually looking at those processes and doing all this computation. And that's kind of what my second point says, that of course you can think about extending. Criticism could be that in our case we only had 3 networks, right? Erdős-Rényi, regular, and scale free. Of course you can think of other network families. That's in a way that's graphs are very difficult, right? It's very difficult to classify them. You know, they are not like model 1, model 2, model 3, right? So maybe there is also scope there to think of a better nomenclature or better classification of graphs. And then, of course, you can try and do this for real networks. Try and take some real networks and see what happens if I simulate dynamics on them. Do they have a very particular signature and you know, what's happening? So yeah, so basically, I think that there is some mileage in sort of setting up systematic and well-designed numerical experiments and trying to understand better and learn more about the process and how what you learn varies with both the network and the dynamics on top of it. In terms of the network, the shipping network, I thought that I was quite excited about that because I think it's a network like none of the one that I analyzed before, because it's a proper sort of physical network. So you have random walkers, which are not random walkers, right? These are ships walking on a network, and then you know the path, they are weighted, they are of different types. They are time stamped because obviously you have a sequence of movements, and it's a bit like you know kids in the toy shop. You don't know what to do. Do you want to focus on the ship? Do you want to look at the global pattern? And I think there is a lot to be done there as well. We were kind of struggling to find sort of metrics and what to plot, what to analyze when you have this kind of interplay between the physicality of the underlying network and the physicality of the actors on the graph. Then you know how do you go about analyzing these things? So yeah, thank you for your attention, and these are my students. Kevin, Andres, and Marco are PhD students, and Federico is a postdoc. Mostly Kevin was the one who did most of the work here, but these are very good guys and we are doing some very good stuff now. So hopefully you see that soon. Well, thank you for your attention and I welcome any questions.
Usually